So the constructor is used to initialize the data members of the object. Typically, a good way to write a constructor is to go through each data member and make sure that you can actually, that every one of the data members is being initialized to a reasonable value. The second thing we learned about constructors was that you can have more than one constructors. The difference has to be in the signatures. So remember we did that example with set. There are two different constructors. One creates an empty set and the other one created a set with one element. And the only difference was that one took no arguments, while the other took one argument as its first element. Similar to that constructor, we have another special function called the destructor. The idea behind the destructor is that it's basically undoes what the constructor does. So what that means is that the constructor, typically what the constructor is going to do is one of the two things. Either it's going to set a data member to a value, or it's going to instantiate memory, which is a very typical use case where it's going to create new memory dynamically. If it allocates new memory during the construction, then we want to make sure that our destructor actually frees that memory up. So for the set example, if you create an elements array, then when the destructor is called, you want the destructor to actually free up the elements array so that the object does not, when the object goes away, everything that it was instantiated and related to the object goes away at the same time, and you don't have a memory leak. Destructors can also take arguments, although that's very rare that you would actually have a destructor take an argument. Typically, constructors are the ones where we have arguments. We did talk about a special kind of constructor worth mentioning. We talked about the default constructor. So the default constructor is a constructor which takes no arguments. The default constructor is the one that's typically invoked when you say something like set A, and we saw an example of that. And you pass in no arguments, what gets invoked is the default constructor. If, when we created the set with say one argument in our example, this actually invoked the non-default constructor which took one argument with the integer. So there's another special kind of constructor, just like the default constructor and the non-default constructor, which is called a copy constructor. So the copy constructor is also very much like a constructor, except that it takes exactly one argument, and that argument is an object of the same type. So for example, if we were to declare a copy constructor for set, so say we are actually writing a copy constructor for a set, its signature is going to look something like this. Set. Notice, like I said, it's very much like a constructor. So the name of the copy constructor is the same as the name of the struct as well. But this is what makes it a copy constructor rather than a constructor, that it can actually, what you actually pass in as the argument, it has to be an object of the exact same type. So you have to pass in a set, and we'll talk about this n% here in a second as well, because it's a new C++ thing. So the idea behind a copy constructor is that, as the name suggests, it's a copy constructor, which is you pass in another set, and what you want is you want a copy of that set created. So I have this object set A. I want set B to have a copy of A. Well, what I can do is I can just instantiate B. I can just type, say, set B, and pass A literally as its argument right here. And what that does is it's actually going to create a set B which will have which will be a copy of A. And what the copy constructor defines is how do you want to make that copy. So what you get is I'm getting another set as an argument, and I'm about to create a new set. So I need to initialize, so the goals are the same. You have to initialize all the data members sensibly, but you have to set them in a way that at the end what I get is something that's a copy of what was actually passed into this. So where is this invoked? Why is this kind of a special case? So copy constructors are invoked when you make function calls. So let's say we declare a set A A, and then I have a function call. Let's say I'm making a function call to function foo, where A is going to get passed in as an argument. Remember we talked about how when you actually pass something as an argument, you actually are basically passing in a copy, because a copy of the variable gets made. Well, when you're dealing with objects, the compiler doesn't want to take responsibility of making the copy, because sometimes the copy needs to be smarter. It can't just be a dumb copy of, I'm just going to take these bytes and copy it over. So what the compiler really does is, when it sees code like this, where A is being passed in as an argument to foo, what it's going to do is it's actually going to check if set struct actually has a copy constructor defined. And if the copy constructor is defined, it's actually just going to call the copy constructor and rely on the struct itself to make the copy sensibly. And simply pass that new object, the return value from this, to foo. So that's the job of the copy constructor. It's special because it is what is used every time you make a function call, a copy constructor, your copy constructor gets invoked. What happens if you don't specify a copy constructor? If you don't have a copy constructor, then the compiler is just going to do a dumb copy, which is it's just going to take all the bytes of A and then just copy them somewhere else in the stack. Literally byte by byte, copy everything over. So if you recall from the exam, in the last question, there was an example where we had a struct which had a pointer to a string, and then we made a copy of that struct. The copy that was made was a dumb copy. It really just copied all the bytes over. And all of a sudden, we actually ended up with two structs that were both pointing to the same string. And that is not what the programmer intended, because when you made the copy of a struct called string, you're expecting that the copy will give you a new string. But what we ended up with in that example was, if you go back to look at the exam, you'll see that what happened was that we actually had one struct and the other struct now both pointed to the same string. And hence, when one of the structs, there was an edit made to change hello to hi, we actually ended up with something else. And inadvertently, as a consequence, the other string got modified because they were both pointing to the same thing. Smarter way of doing that, you have a copy constructor. When the copy is actually made, you actually make a copy of the string, create a new string, so that the first struct pointed to hello. When we make the copy, we allocate new memory and copy the contents over like this. Now, if this struct edits this hello to a hi, there is no side effect to this guy, which is how you intend it to be when you make a copy of a string. What you don't want is a string, I want to make a copy of the string, and now when I change either of those copies, both of them change at the same time. That's not very valuable. You want the copy to be a true copy. But the dumb copy that the compiler made in the case of that question, and the way it was phrased, if I remember correctly, was just S1 is equal to S2. The compiler simply took all the bytes in S2 and copied them in S1, including the pointer to the string. That's how we ended up with both S1 and S2, essentially pointing to the exact same bytes. A smarter copy constructor would have written something like this very differently. And in fact, since we have the set example, let's try to write a copy constructor for a set. So we have a copy constructor. We know that this function, its job is that there's another set, a reference to another set being passed in, and we want to initialize the object. Remember that there is an implicit this here from last time. So what we need is everything in this object gets initialized such that it's a copy of S, but it's a sensible copy of S. So let's first do a dumb copy of S. What I'm going to say is I'm going to say this to the length is equal to S dot length, and this to the elements is equal to S dot elements. Is that a copy? Is this object a copy of S at this point? is that actually it's a sensible copy? Is it a smart thing to do? What happens when S goes in and updates the elements array? It does an insert on S. When an insert will happen on S, what's going to happen? It's going to change the elements array for the current object as well. Yep.
Should that be a arrow over there instead of
for the S right here?
Yeah, because I assume like a S
Yeah,
is
it should be.
address.
So there's actually, this is actually a C++ thing. We will actually get to that in just one moment. If an arrow makes you guys feel more comfortable, we'll go with that, but I'll come back and correct this. It's a separate topic that we'll get into in a second. C++ introduces a brand new concept of passing in these and copy by reference, so we'll get to that in a moment. Yeah.
I'm kind of confused. What's the difference between S and this here?
So this is the object. So here's what's happening, right? So great question. When is a copy constructor going to get invoked? So one example of when the copy constructor can be invoked is when you do something like this. If A is a set and B, I'm creating a new set B and I want it to be a copy of A, this will invoke the copy constructor. Why is this going to invoke the copy constructor? Because a set is being passed and a set is being passed. So the signature matches. Now what is this going to point to? Which of the two objects? This is going to point to B because that's what's being constructed and A is what we are trying to get a copy from, which gets passed into this. So this is B and S is really copy of A. That makes sense. And so this is a dumb copy, clearly. What would be a smarter copy of a set? And you guys have it in this code already, I think.
Allocate.
So what you really want to do is you want to allocate a new array for this to the elements. So we'll just do int star malloc. Again, the same thing, size of int times this to the length, since I just passed in the length. So now this to the elements is a new place in memory, and then we'll have to write a for loop or something where we can just say for int I is equal to 0, I is less than this to the length, I plus equal 1. And inside this for loop, we just need to copy all the elements from S to this, which would mean this to the elements of I is equal to S, and I'll just go with the arrow notation for now, but you guys will see in a moment why what I had done was more accurate. Elements of I. So now this is actually a sensible copy, and now we have a copy constructor. Now when we do set B of A, it will make B a copy of A, but a sensible copy of A. If you don't need anything special happening in the copy constructor, you don't have to write a copy constructor. You can just leave it, and the compiler will make a dumb copy, which is just a byte by byte copy, like it would do in C. In C++, we have the opportunity to override how the copy gets made. Question?
Professor, this dot elements equals to S elements. Why is that not a smart thing to do?
So this to the elements. So let's dive into that.
We are basically achieving our goal, right, to copy the elements over.
So we have A and B, right? So let's start with A. So A itself has two pieces, as we know. One is the length. Let's say the length is 4, just for the sake of argument. And the other piece is elements, which is a pointer to an array with 4 integers saved in it. Say 0, 1, 2, and 3. This is what A is, just for the sake of argument. If you just did literally what I call a byte by byte copy, which is I copy the length over and I copy the elements over, what's going to happen? What is really saved in elements? It's a pointer, right? It's a pointer to a 4-byte array. If I just make a copy, if I just did this to the elements, I will get this picture, which is, now B also has a pointer to the same array.
Oh.
And I will copy the 4 over. Now, what is the problem with this? Now, later on down here, if someone did A and A to the elements, or A dot elements in this case, A dot elements, of 0 is equal to 9, that would actually change this 0 to a 9, and inadvertently, now B element 0 has also been changed. Not something you want. Unintended consequence. So for that reason, we actually want to make a copy, first create new memory and then do a copy of the entire array one by one. You cannot just do, and this is true in general for arrays. If you have two arrays, if you just do A is equal to B, it does not really copy the entire array over. Because remember, never forget that array variables are really just a pointer to the first element in the array. Question?
Why is it that you passed in A itself instead of its address when you make the
Pass in array, so let's jump into that. So now that we have, first let's make sure that the copy constructor is clear. Then we'll get into this new syntax thing here that I'm kind of hand-waving over still.
also that A is related to
Yeah, so that is also related to this. So this is basically what the copy constructor is. So again, trying to answer the same two questions for the copy constructor. What is it? What does it do? It makes a copy of another object for you into this pointer. When is it called? It's called either when the programmer explicitly writes a statement like this, where you know that you want a copy, or it actually is called when you make a function call. Inadvertently it gets called. You don't even realize it, but under the hood the copy constructor gets called. Make sense?
I don't get that syntax about set.
Set B of A.
Yeah.
So set is the type, B is the new variable we are creating named B. And you can actually, we actually saw an example of that last time, that sets where you can actually pass in an argument like this. And what this does is it actually calls, when the compiler sees this, you have to kind of wear your compiler hat for a moment. What is the compiler seeing? The compiler sees this as you're trying to create a set named B, and you're looking for a constructor which takes another set as an argument. And if a constructor like that does not exist, it's going to come back and complain. But in this case, it will find another constructor that looks like this, and hence it will just execute this constructor, which is a copy
It
constructor.
knows A is like that.
Exactly, it knows because that A is like that, precisely. Make sense?
Yes.
Any other questions? Yeah.
what would be this if we're like making a function called like foo of A? Well,
If we do foo of A,
yeah.
just like that.
Yeah.
Well, if you do foo of A, there is no this here, because foo is not a member function. If foo was a member function, you can't just call a member function like this, remember? I'll never forget that. The member function will always be called either as a dot foo, because I have foo being called on an object A, at which point this will be an address to A. Or if A is a pointer, a member function will be called like this, in which case, again, this will be an address to A.
No, I mean like when we do like foo A, that constructor is gonna be called, right?
That's right.
And then
Okay,
in
I
that
see what you're saying.
constructor, what would be this?
Okay, that's a great question. So the question is, when we just write foo of A, and let's just write it here instead of over there so that it's very clear what we're trying to do. When we call foo of A, we have all agreed that a copy constructor is going to be called because the compiler is about to make a copy. So what is S going to be in this case? We know that S is going to be the address of A. It's basically A. The second question is, what is this going to be? So the way it works is that the compiler just creates a temporary object. You don't give it a name. The compiler just gives it a random name internally and just uses that. So it's not really a variable that you are declaring, but there is actually a portion of memory that gets reserved for it. So if we open up our activation frame, you will see a copy of A sitting in memory. It's just not a variable that we create. And this happens under the hood even in C. It's not C++ specific. Anytime you pass in a function with a variable, that variable gets a copy made and then run inside the function.
And then how can it be deleted?
How does it go away? It's a great question for you. The copy, so question back to you. We just created a new object which is a copy of A, and on that copy foo is run, right?
As soon as
When will it actually get destructed? As soon as foo ends. That's exactly the idea. So that's when the destructors role comes in. So a destructor for this copy constructor will have to set length to 0, will have to free up the contents of the element array. So in my constructor, I did a malloc. In my destructor, I have to do a free to be equivalent of that. Make sense? Yep.
So just to double check the differences, but
Sure.
we did set A, we we make a pointer that A is pointing to, and then we have empty spaces. Whereas if we declare set B with constructor, we fill in those spaces with whatever inside the instructions for the copy constructor.
So good question again. So the question is the set A, we are basically creating an object on the stack in this case, because we're assuming it's a local or a global variable, so not in the heap. In the first case, you create a certain set of bytes. Actually, we know exactly how many bytes. If pointers are 4 bytes, then it's going to be 4 bytes for the pointers, 4 bytes for the length. So 8 bytes of memory gets reserved on the stack. But then what happens? Your constructors, the compiler will go and look for, what kind of constructor will it look for in this case? The default constructor. So it's not what you described it to be. It's not that it's just 8 bytes of memory with not knowing what the value is. If a default constructor exists, it is going to get called, even for A. For B, it's going to call the copy constructor because of the way it's written over here. Now, again, there could be a variable C, which actually takes in the number 1 as its argument. In this case, that other constructor that we wrote last time, we took integer k as the argument. That's the constructor that we're going to call. So when the compiler sees set and a variable name in front of it, it looks for constructors. If none exists, it just ignores the constructor call to the constructor, which is how your C structs used to work. When you declare a variable, there was no such thing as constructor. In C++, the compiler looks for a constructor. If a constructor exists, it checks if it's of the right type. So for example, set A, it will look for a default constructor. For this statement, it will look for the copy constructor. To service this statement, is going to look for a constructor that takes 1 argument, which is an integer. And if it does not exist, it will buff back. If it does exist, it will just call the constructor. So it chooses the appropriate constructor based on the arguments given. No arguments, 1 argument, 1 argument, 1 argument of type set, 1 argument of type integer. Choose the right constructor and just call that.
Is that the maximum number of constructors, or we can?
You can have as many as you like. Yeah.
Well, the bottom foo A, that's not a copy constructor.
No, that's just a member function being called here. So yeah, the syntax is a bit wacky in that if you see the type over here, then this is a variable name and these are the arguments. Here, this is just a regular function call in C. This is something that did not exist in C. In C, you could not put type name and then put a variable and then give it arguments. It's going to fail pretty miserably. In C++, if you give it these arguments, it's going to look for that constructor. That's the difference between C and C++. And remember that anything you could do in C, you can do in C++. You can just not have a constructor, and then your set A will work exactly like it would work in C. It's just a blob of bytes created with the values initialized to random bytes. That's how we always assumed it to be in C. In C++, there's an extra feature that if you have written a default constructor, it will get called automatically. Make sense? Yeah.
So if you call set A and you don't have a default constructor, but you have like other constructors, would it still be there?
If we did not have a default constructor, in this case, it would not throw an error. It will just create a bunch of bytes, just a blob of bytes. It will just not initialize them. Default constructor won't be called.
Okay,
But for the other ones, if they don't exist, it will complain because it does not know how to make those calls. The default constructor is just that simple. Just create a bunch of bytes for you. Very much like the C struct declarations. Other questions? Yeah.
If you can do S dot lengths instead of S arrow lengths.
Yeah, so let's dive into that. Just hold on to that part. Any other questions? Okay, so let's deal with that because that's a pretty much a topic in its own. Between C and C++, there is a subtle difference which goes beyond just objects and constructors and stuff. And it's the body of knowledge, we refer to it as pass by copy or pass by reference. So remember in C, there were 2 ways of passing a variable to a pointer. When we talked about variable to a function, when we talked about pointer and functions, remember that we said, I can have a function foo that actually looks something like this. Let's say that foo takes in as its argument an integer a. Let's not call it a, an integer x. That's a standard function in C, right? Typical function call, nothing special about it. If you wanted a function bar that you want to have the ability to actually edit the contents instead of passing in a value, you could actually pass in a pointer, right? There's two ways you can do it. You can pass in a variable, or you can pass in a pointer to the variable, to a function, depending on if you want the function to be able to change the variable or if you don't want the function to be able to change the variable. In C++, there's actually a new kind of, there's a new way of doing this, which is, so I'll just call it foo C++. Now, this is clearly different from star y, and this is clearly different from x. There's actually a brand new way of calling functions and declaring functions in C++. Again, the older ones still work the way they do, no changes there. But the pass by reference is a new mechanism where you, so here's why this exists, and that's the easiest way to understand it. So remember that there were two things that we used to do, as we know. We used to pass in a variable by copy, and we used to pass in a pointer to the variable. Here is how the functions would typically look when we would have them. So I'm just going to draw a line and talk about the first two options, the C and C++ options. So one option is we have foo, which takes in a variable x as the argument. And the second option is foo, which takes in a pointer to an integer as the argument. Now, inside of the function, here I can use x however I like. I can do x plus 3 and just return that if I wanted. What I cannot do is actually change the variable that was passed in. So here, let's do this actually. So when I'm calling this function, foo, I will either call it like this, foo of a variable called x. In this case, if I'm calling foo, I'm going to have to call it foo and the address of x, right? If I want to use return x plus 3, I can just use x conveniently, no fanciness required. Here, if I wanted to accomplish the same thing, I'd have to do star x plus 3. Right? These two functions are completely equivalent, just that their calls are going to look different. Right? Any questions? Because this is kind of fundamental to the whole pass by reference. If this becomes clear to you, you'll get the next piece very easily. So these two functions, I mean, their effect is going to be precisely equivalent at the moment, because in both cases they will return the exact same value. If this is what's confusing you, you can fix that.
No, I mean, that's going to change the variable x that we see.
No, right now we are not changing any variables here, right? Nothing is on the left-hand side of an equal statement.
Oh.
Here we are just doing return x plus 3. Here we are just doing return dereference of y plus 3. Right? Any confusions or questions on this? All right. So with C++, they saw that this is clearly the more convenient syntax. You don't have to deal with putting that asterisk. Recognizing the fact that this is a pointer, you're just that simple. I have x, I'm just going to do x plus 3. Like you pointed out, what I cannot do over here is, what if I did something like x is equal to 2? Will that actually change the value of the variable x that was passed in? No, because this only is going to operate the copy. If I really did want to do that, I would actually have to do star y is equal to 2 over here. Now these functions are not equivalent to your point earlier, because in this case, the variable x is actually going to change. In this case, the variable x is not going to change, because what gets updated inside the function call is just a copy. It's not the actual variable. Remember that when foo is called, we just went through talking about the copies and stuff. The compiler is going to make a copy of x, pass that into foo. When we actually update it in here, it's not going to come back with the value of x changed in any way. They're not equivalent anymore. So here's kind of the trade-off. Convenient syntax has a major shortcoming. You cannot change the variable. inconvenient syntax has a major benefit that you can change the variable that gets passed in. This code was happening quite often in C. People were passing values into the functions as pointers, and actually then having to dereference the pointer everywhere as your code would be written. So they said, well, can we make this functionality with a convenient syntax like this one? That was really the motivation for doing the %. So from there, a third kind of function call was born, which is really trying to get the best of both worlds. The way it works is, I will declare my function foo as int foo. Instead of using either of those two syntaxes, I would actually use a brand new syntax by putting an %, here. Now in here, I can actually just do x is equal to 2, return x plus 3. See that the code for this and this is precisely the same. There is no changes. And I can actually call it like this as well, as foo of x. So the code between this and this, what is the only difference between the two codes? Literally is only one difference, the use of %, over here. What is the answer for this function? X continues to be whatever value it was. The return value is going to be 5, right? Here, return value is 5, but x will actually get changed, and that is the difference between these two functions. At the end of foo of x, if I actually print x, I will get x is equal to 2. Here I will get x whatever value it was before it was copied into the function. So I'm getting the functionality of this ugly syntax with asterisks everywhere, and the %. I'm getting the cleanliness of this syntax, but the functionality of that, and that's really what the pass by reference in C++ is. You actually act like you by putting that %, you're basically telling the compiler, whenever I use x, under the hood, the compiler is really just going in and putting that dereference for you. It's just taking care of the dereferencing for you. And when you call that function, the compiler is putting that %, for you. So there was a lot of ugly characters that we were having to type, the ampersands and the asterisks everywhere in our functions. C++, just put one % on top, the compiler will take care of everything else for you. If you decide that I really don't need to pass x as a reference anymore, now these two are exactly equivalent. If I decide, damn, I wrote this function, I did not realize that I should not have passed in x, I should have passed in a pointer to x. It has happened to all of us at one point or the other. Very easy fix now, just put an %, and now you get your result that you wanted. Whether you want something passed in as reference, whether you want something passed in as copy, the only difference is just put the %, the exact same thing, and the rest of the code stays exactly the same. So you can convert one to the other a lot easier, versus here, conversion from here to here would require changing all the function calls and the entire function. Conversion between here and here, one character added or removed, and you get one versus the other. And the functionality is, so this gives us a more powerful functionality of that, while the syntax is clean and it's easier to transition between the two options. So that's basically the motivation for having it, and that's exactly how it works. Is just that the % makes it behave like this guy, while having the cleanliness of this guy. That's really what it is. Yeah. Start with you.
So you're saying that the first and 13 compile to the exact same code?
And under the hood, that's a great point. The first, with this one with the %, and the last one with asterisks, is actually absolutely right. They will actually compile to the exact same code. If you actually look under the hood, the compiler is going to take this, turn it into that, turn the function call into that, and then compile the code for you. It's really the compiler just doing the heavy lifting for you, so you don't have to deal with a lot of extra typing. And a lot of extra mental energy spent in asterisks, and do I need an asterisk, do I not need an asterisk? It was basically, a lot of this is programmers being lazy. Just I don't want to type the same thing over and over again, there's no value. Let's make it a feature of the compiler so it just happens for me automatically. I'm doing it so many times that I just went ahead and added a new feature in the language to handle that use case. But that's really what it is. Question?
Yeah, I just want to ask, return x plus 3, not changing the value of x over there, right? You're just changing the value of the actual x when you do x equals to 2.
So if with the %, we are actually changing the value of actual x, and yes, this will be 2 plus 3 because we are changing the value of x.
But the original value of x won't.
It won't be there anymore. I mean, the original value of x got overwritten by doing
By
this.
2. Right.
Yeah. So if I print x down here, we'll see x is equal to 2. Yeah.
In the pass by reference, say that the x is an array, is a pointer to an array. Aren't we like what? So we can't do any more like x plus 1 to go to the next memory location, right?
Yeah. So that's kind of the next order question. Just hold that thought for a second. I want to make sure we deal with basic questions first.
So like over there, since you're being passed in the address of x, you're actually going into x and putting it into.
Yeah, you're actually going into x. You're dereferencing it and actually putting it. The compiler is really, so the point was very well made, is this code and this code, if you look at the underlying assembly, will be exactly the same. It's really just a convenience thing. It's not really it's not changing how computers work, it's just changing how you can add fewer characters so you can be a little lazier. That's really what the compiler is doing for you. Question?
So like, what if you have like a 2-dimensional arrays or like,
So we'll get to arrays in a second. Any other questions? Yeah.
So for the middle one, you just write x equals foo of x, and the same thing.
Sorry, say again?
If you just set x equals foo of x, that'll do the same thing.
X is equal to 2 of x.
Or foo of x.
X is equal to foo of x.
On the middle one.
X like this.
Yeah.
Yeah, this will actually lead to x being set equal to 5.
So it'll be the same thing as doing as the bottom one, right?
Yes, in this case, in this case, x is going to get returned as not as 5, right? If I print x right here, what is the value of x? If I did a printf of x right here, what will I see for x? You'll actually see 2 because x was set equal to 2. So the way you're going is right in that it's basically turning much closer. But here x will be equal to 2. If I print x, I'll get x is equal to 2. Here, if I print x, I'll get x is equal to 5 because it's 2 plus 3. What's that? Any other questions besides the arrays? Not a question. So, all right. So we're talking. Let's get into the arrays and how we actually deal with them. So it's actually a pretty big convenience factor there too, kind of the same way. If you want to pass in an array, so and say what we want to pass in is an integer array. So what we really have to do is just, when you call this function, if I have declared an integer array, say int a of 10, so this is the function, this is the call, I can just say foo a, and in here, if I want to access any elements of the array, I can just do them as, say, array of 0 is equal to 10, something like this. So it's a relatively convenient syntax. It's not really a pointer. You don't have to do +1s, +2s. You can do something just like this. Array of 0, array of 1 is equal to 5. And you basically got a reference to an array, and then you can use it just like an array variable, just like outside. So the idea is what the ampersand pretty much does is it allows you to use that variable exactly the way you would have used it over here. Now you can use it inside the function as well. And it's the same variable, so the copy is actually, the value, it's not a copy, but it's the real variable, so the things actually get updated. Under the hood, the compiler takes care of the dereferencing and +1s and -1s for us automatically. Answer your question? You had a question about 2-dimensional arrays. Was there anything specific you were thinking?
you like a pointer to a pointer or something?
Yeah, so again, the same thing. If you actually had a pointer to a pointer, you just have to declare, the key is that, so this is typically used, you would typically not use it on top of pointers, like arrays is kind of a specific thing. But the key is always to remember, and this is kind of a more generic thing, this is how I would use variable a over here, however I want to use it. I want to dereference it, if it's a pointer to a pointer, then I can dereference it over here to get my array, for example. you can use the exact same syntax to access that variable in here as well, and the compiler will do all the magic and transformation for you. The extra level of dereferencing. So if it's a pointer to a pointer, you can actually use it like a pointer to a pointer. The compiler will take care of that extra, passing in that extra level of that extra level of dereferencing for you. That's basically what it is. What's important to remember is it does only one level of dereferencing for you. What it does not do is multiple layers of dereferencing for you. So it will just add one asterisk for you automatically, but it will not do is add 5 asterisks for you just because you're passing in a pointer to a pointer to a pointer to a pointer. It's just going to dereference one layer for you. But that's the key. But very rarely would you actually see something passed in with an ampersand, which is actually a pointer. Typically we use the syntax for just variables. We typically not use it for pointers. Because usually, again, when you're passing a pointer in, you don't really want that pointer to be modified. Usually when you're doing that, what you want modified is the thing that the pointer is pointing to, which implies that you don't need that ampersand anyways. If what you have is a pointer, just pass the pointer and just use it inside. Just like you do in C. So you would not really use this syntax if what you had is a pointer. Where this syntax is handy is I have an object like we had set over there, and I want to pass it into a function. Now let's come back to this example, because this will now make sense. And now this will make sense what I was doing over here. This was passing in a set with an ampersand s. It was passing in by reference. The set s is being passed in by reference. So inside this function, I can really use s like it's an object, and the compiler will take care of the dereferencing for me. So what I can do is I can just type s.length, and that would actually imply that the length of s will be obtained. In here, I could actually do s.elements, and that would actually take care of, the compiler will actually take care of this. If you actually put in the arrow syntax, the compiler is actually going to complain that array is s is a reference, it's not a pointer, because you're supposed to use it like a reference, which is like a variable, not like a pointer. Under the hood, what is the compiler really going to do here? We do know what that is. The compiler is going to really say, this is really a pointer, and I'm going to dereference it and then call .length on it. So, but the key is that we're going to use it with a dot. That's because we are passing it in with an ampersand. So when you pass something as an ampersand, you really want to use it like it's a variable, not like a pointer. That's a critical piece.
So if you use asterisk over there, we're going to get errors.
Yeah, so if we actually used like dereference of s, for example, or what do you mean by asterisk?
Yeah.
Like if we try to do a dereference of s, yes, we will get errors. It's going to say it's a reference, it's not a pointer. So you can't dereference a reference. You can't dereference a reference. That's a distinction between reference and a pointer. This is it's just a C++ terminology. This is a reference, as opposed to a pointer, which is the one declared with a star syntax. So the compiler is going to say the arrow syntax is for pointers. For reference, just use the dot syntax. So again, just quickly recapping that aspect of it. When you have an object itself, like you declare set s, use the dot syntax. When you have a pointer, use the arrow syntax. And when you have a reference, which is something declared with an ampersand, you should use the dot syntax again. Make sense? This is part of the convenience factors, because the arrow takes 2 characters, the dot is 1 character. You just don't have to worry about the fact that it's a pointer. You can just use it like almost like a local variable declared in here, except that it will act like something that will actually update the real variable. The compiler will take care of the dereferencing. Replacing the dot with an arrow, all of that will be taken care of by the compiler for us.
So this only adds convenience, it doesn't add any like functionality.
It's not really something that you could not do. You could have done all of this before with pointers. In fact, between the three, the pointers are by far the most powerful, because you can really control whatever you want to do. But it's a lot of ugliness to have to put those asterisks everywhere in your code. So the idea is you really don't need that power all the time. So when you need a copy, you use a copy. When you need a reference, you need to use a reference. And in C++, good C++ code barely ever pass pointers to functions. You'd either parse a copy without the ampersand, or you'll see a reference passed in with the ampersand. Rarely you'll need the pointer, but that's a more weird scenario. Kind of like what he was describing, the 2-dimensional arrays. That's one example where you probably pass a pointer still. So now does this help close the loop on the copy constructor? Why I had the ampersand and why I used the dot instead of the arrow? but the essence of the copy constructor still stays the same. You're basically passing it a reference to another object, and the copy constructor makes a copy of that object. And it'll just take care of that for you. Yeah.
Say we have a two-dimensional array, and then inside of the argument for the function call, we pass in like a bracket zero, not the address of a bracket zero and bracket 0. Would that work?
So if you pass in, so what is, so the question is, whatever I have a two-dimensional array A, let's say 10, 10 maybe, fair. And what happens if I try to pass in A 0, 0, 0, 0? What is the value type of A 0, 0 by the way? It's just an integer, so it can
No,
be
the
passed in.
address of that. Like,
Oh, if you passed in the address of that. So that's really the same thing as the variable A, it's the address of array. Remember that array is the only wacky thing where the variable is really the pointer. So it's really this and this are actually the same thing if you look them up in the debugger. A and address of A00 are exactly the same thing.
So if I send that, then I can, like in that.
So a good compiler will probably buff back at you because this is really a pointer. If you just passed in A, that's really an array variable. And Visual C++ does not let you use these interchangeably in general. It would actually buff. Even though they're both the same value, the compiler will actually buff back at saying you're supposed to pass in an array, not pass in an integer pointer. Because this is really an integer pointer at this point. Well, that's a two-dimensional array.
So if you pass in the A itself, then we can use it.
Then we can use it with a reference.
With the reference, we can just use a bracket. whatever.
Exactly, A01, just like you would use it outside. That's kind of the rule of thumb to remember. When you pass something in as a reference, it's not any different than passing it in as a copy in terms of the code. The only difference lies is the %, and now you have the ability to change this if you wanted within the code. If you did not have the %, now you don't have the ability to change this guy. Make sense? Alright, so important concepts here, copy constructor, we nailed that one when we talked about pass by reference. Pass by copy, pass by copy is where the copy constructor gets called. So one thing that I've also been kind of glancing over is, I mentioned this to you guys last time, which is the malloc. Malloc is actually a C thing. C++ has a better way of dealing with dynamic memory. There are two new, instead of malloc and free, we actually get two new constructs. The two new constructs are called new and delete. Is this color visible, by the way? So we get two new constructs, new and delete. So what new is it's actually quite simple. What new is it's basically, under the hood, it's a malloc followed by a constructor call. And what delete is, it's actually a call to the destructor followed by a free. So if you look under the hood, when you call new, it's really going to mean two things. It's going to first malloc and then call the constructor, the appropriate constructor. If none exists, then it does not, nothing happens. And when you call delete, it calls a destructor if it exists, and after that it calls free. The ordering is actually critical, these are not random. So first you allocate memory, then call the constructor. First you call the destructor, then you free the memory. And the reason that's important is you cannot initialize data until you have allocated memory for it. Remember, the constructor is about initializing data members. And you first want to make sure that you use and delete everything, any kind of memory that was allocated before we call free, because after we call free, you can't go back and access its variable, it's being destroyed. It's at free at that point. Question?
So when you use delete in your destructor, you wouldn't want to write a free, because then you're not.
That's right. So when you use new and delete, you forget about, you don't use, this replaces things that you guys know about malloc and free. You can still use malloc and free in C++, there's nothing stopping you, but malloc does not call the constructor, and similarly free does not call the destructor. That's the way C works, And remember that we are designing the C++, make sure that anything in C continues to work the way it used to, and you'll see that everywhere. So instead of changing malloc and free to now call the constructor and destructor and changing the way the languages behave, they added a new construct called new, which calls malloc and then calls the constructor, and then a delete, which calls the destructor and then calls free. So, and there's also some convenience in terms of syntax. Question?
Yeah, destructor and constructor, what structure is that?
What structure are you talking about?
Because you said that destructors and constructors are only for structs, right?
Yeah.
Which structs are we talking about here?
I mean, whichever one you want to call the malloc, the
Inside
new
here?
and delete on.
Oh,
So let's create one for, let's create a simple, so this is how you use new and delete. So this is what they are. Let's talk about how they're actually used. So the way you use new and delete is, let's say I want to have an integer pointer A. I want to equal, and I want to create an array of 10 integers, dynamic memory for A. How would I do it in malloc? I would actually then do int star malloc size of int times 10. Right? That's how you guys have done it so far. C++, this is how you can actually do it. Int star A is equal to new int 10. Exact same thing gets done with fewer characters. You just say new, type, and then the size, and it'll take care of creating that array for you. In addition to that, int incidentally is a type that does not have a constructor because it's not a struct. So what's going to happen? No constructor is going to get called because it's an int. Now let's say that I had done it for the same thing with a set. I could have also done set star s is equal to new set. Now this will actually create an array of 5 sets, where each set, it's going to call the constructor on each of the elements on its own. So instead of malloc, if I use new, I actually get the malloc and the constructor call happening automatically. By the way, just out of curiosity and just checking your instincts, what constructor is going to get called on the 5 elements that will be default? The default constructor, because it wouldn't know. But what if I actually did, let's use a different number. What if I did this, just based on what you guys know, what is this going to do? It's going to create an array of 5 sets, where each set is going to call the non-default constructor. Which of the 3 constructors that we have done for set will be called here? Remember that there's a default, there's a copy, and there's one that took integer as the argument. The one with the integer, which is creating a set of size 1. So this will give us 5 sets, each containing only one element, which the value of that element will be 6. It will automatically get called for us. So that's how you use new. It's just a more convenient way of saying the same thing. Rather than actually saying int star malloc size of int times 10, you just say new int 10 creates an integer array 10. You can call the constructor and rely on the constructor getting called. You can use it for types which do not have a constructor, that's fine, nothing will be called. If there is an appropriate constructor, it will actually get called. Now how do you delete? It's actually, there's 2 kinds of delete. One is where you can actually delete a single value. So let's do this example. Set star t is equal to, if I did not want an array, I just want a single set, I can just do this. Set star t is equal to new set, creates 1 set. And this will basically, again, call malloc for 1 set and then construct. Yeah.
So like the difference between like using new and just using a single set is like when using the new is gonna create that thing on the heap.
Yeah. So new is anytime you use new, it's going to create it on the heap, and that's right. Between say calling set of A, when you do this A is actually going to land up on the stack, unless you're using global variables. But we have set a big no-no on that anyways. So that will create it on the stack, but this will create it on the heap. New is always going to work like malloc, because under the hood, never forget that new is nothing but malloc followed by a constructor. So I say new set star t is equal to new set. New means a malloc's going to get called and then the constructor is going to get called on it. Make sense? There are two kinds of delete. In these two situations, we actually run into a kind of a subtlety that's very, very easy to miss as well. If you declare a variable, like we did over here with a single object, you can just simply call delete of t. It's just written like this, delete space t, and this will delete. This will basically delete, and delete is call the destructor and then free. However, if you want to actually delete something that points to an array, an example of that would be our variable s over here. There is a special delete for that, which is delete followed by 2 square brackets and s like this. So you actually get delete t and you get delete array at this point. So you call new, typically one variable gets created like this. If you want to create an entire array, you put the type and the size. If you want to call a special constructor, the arguments can go right after over here. When calling delete, you have to know whether the variable is pointing to an array or a single object. If it's pointing to a single object, just delete value. If it's pointing to an array, delete. This is often referred to as the delete array operator. So you do a delete array and then put the array pointer in front of it. So this is where a major subtlety exists, because with free we did not have to make that distinction. With delete you do. And what delete does, it first calls the destructor. So in this case it calls the destructor on t. In this case it calls the destructor on all 5 elements in array s. And then it calls the free, which just frees all the memory. Yeah. You can go ahead first.
Me?
Yeah.
Oh, what if you like delete something in the array and then you call delete s?
If you call delete something in the array,
Yeah, like because
Like, try to
s
do
is a set of array of sets.
so if you're trying to do something like delete of s0, are you thinking?
Yeah.
So if you call something like delete of s0, or maybe make it more explicit, let's say delete of s1, this one's actually going to fail. You guys, I mean, nothing has changed conceptually. Under the hood, it's nothing different than this. It would be like calling malloc on a pointer that does not point to a new block. So your signatures are not going to match. Remember, the signatures are on your allocated blocks. So you'll actually get a free error saying you're actually trying to delete something that's not the start of a memory block. So you would actually just get the same. It's the equivalent of the error that you will get if you try to call free on a random pointer, if you will.
What if it's delete s?
But if you actually do delete s, still the same thing. You will actually get an error. It will actually say that you should be using an array delete array rather than a regular delete. So that's why you want to put the delete array. It just wants you to be explicit that you are calling destructor on multiple objects at this point. And that's the major difference, right? There's this, under the hood, compiler is really generating a for loop for you and going through the array and calling the destructor on every one of your array elements. It's taking care of all that for you. But it wants you to be explicit that that's what you really want. Yeah.
Earlier we had a new set bracket 5 and in parentheses 6. Was that basically making an array of 5 sets and then setting the
Calling the
first
constructor on each one of them, the first element to 6.
the first element of each set. is
That's right.
6.
Yeah, and in fact, on that note, let me just do a quick quiz here. What if I actually wanted to do a set t as new set? This is a set, right, at this point. What if I want to make it so that the new 5 elements that get, new 5 sets that get created here are really just a copy of that?
Just pass
Yeah.
t as those.
Parentheses.
The address of t.
So we all agree that there's going to be some form of t here. So the one person suggested and of t. One
Just
more.
t.
Just t. So remember, the copy constructor is right here. It hasn't gone anywhere. For the reference, what do we expect when you want to make a reference call? What does it expect? Does it expect a pointer or does it expect a variable? It expects a variable. Do we have a pointer? Do we have a variable? So what should we do to make it a variable? You have to dereference it. But and will actually get you the address, and does the exact opposite effect. If we dereference t like this, this will create a set of 5 elements where each one of them will just be a copy of T, of this set that we created over here. Make sense? Because when you're passing something as reference, you have to pass in a variable, you can't pass in a pointer. The compiler will, under the hood, do all that funky stuff, we know what it's doing, but that doesn't mean that it's going to allow us to do it however we want. There's a very specific thing you can pass in, then the compiler internally will convert this into a pointer and take care of passing everything in correctly. Yeah.
So delete knows how many times to call the destructor. Does the compiler keep track of it, or is that information stored on the stack?
That information is stored somewhere in the heap itself. The heap knows how many elements are there. Well, it's not necessarily the heap, it's other portions, metadata that actually gets saved, that is basically keeping track of how many elements are there, and that's how many times it's actually going to call. So it knows that this particular pointer points to an array of size 5. So it takes care of all that. Remember that you have had to do that yourself in the past. What we typically did was we actually kept this information either in the programmer's head, which is kind of a bad practice, or in a separate variable called length or something like that. Here, the compiler is being nice in that it's taking care of it for us. All we have to say is declare an array and delete an array, and it'll take care of constructing all of them and destructing all of them. We don't even care what really is happening in between, essentially. It's just taking care of it. Other questions? So just getting more and more into C++. So we've talked about, again, just a quick recap for everything we discussed today. So we talked about, we did a recap on constructor and destructor. We talked about another special kind of constructor called the copy constructor, which led us down the rat hole of what does pass by reference mean. Pass by reference is, it's critical to sort of have these 3 examples in your head. That's the easiest way I always remember it. This is the best of both worlds, the convenience of this guy and the feature set of that guy. That's basically what you get. And a really easy conversion between one or the other. Much better than converting between those two. It's a lot easier to convert between these two. This is pass by reference, this is pass by copy, and this is what pass as a pointer. That's the 3 variations. So we talked about that, then we kind of jumped into how do we deal with dynamic memory. And this also answers another question. Remember last time we kind of left it vague. There are 3 cases in which the constructor gets called. Remember we talked about that? What were the 3 cases when the constructor gets called? First, when a global variable is declared of type. Second, when a local variable is declared of a particular type. Remember that conversation? Third, when you actually call new. That's when the constructor gets called. What are the 3 cases when the destructor gets called? Can someone fill me in? Equivalent to global variable. If I declare a global variable of type set, when will the destructor for that variable be called? When the program ends. If I declare a local variable of type set, when will the destructor for that be called? If I create a dynamic set, set in dynamic memory like this T over here, when will its destructor be called? When I actually call the delete T, it will automatically call it. Remember, delete is destructor plus free. So that kind of ties the entire loop. Any questions?
So that's the only case where you have to specifically make sure that it gets deleted?
Yeah, you have to make sure that yes.
You have to
Global variables go away on their own, local variables go away at the end of the function. But when you put something with, just like you create something with malloc, when you create something with new, you have to call delete yourself. And as long as you have this table in your head, new and knowing that you guys know malloc and free, it's actually pretty easy to remember this. All it is malloc plus followed by a constructor. Constructor doesn't exist, that means nothing happens, like the integer example. Similarly, destructor and free, destructor doesn't exist, nothing happens, only free is called. Make sense? Yeah.
Can you forget what exactly happens in the destructor?
So the destructor is when you, it's a function that you write that we talked about last time, which has the tilde in front of its name. And a destructor is called when a variable is, one of the 3 cases again, when for a global variable when the program ends, for a local variable when the function ends, and for a dynamically declared created variable when a delete is called. And the destructor is a function that you write. If it doesn't exist, the compiler doesn't do anything. If you write a destructor for the set, the destructor is going to be of the form So it's going to be a member function of set. That's why I'm going to use set colon colon. How the compiler knows that this is a destructor is because you're going to use the tilde in the name. Typically, destructors take no arguments. Everything is a default destructor. And inside of here, we will, now that we understand new and delete, I'm just going to do delete elements. And that will actually be the destructor for set. Just set delete elements. Delete, remember I noticed that I used delete array elements, and that'll actually get rid of the elements inside the set. Answer your question? So it's really just a function that you write. If you don't write one, then the compiler is not going to do this for you. And if we were to, since we are on the subject, remember that there was a unity, and let actually we can just do that. So we can actually go back and rewrite our copy constructor, for example, now that we have new and delete in our toolbox.
Can I ask a question before?
Yeah, please go ahead.
Over here, when we're declaring S, first we're allocating spaces for all those 5.
That's right.
spaces.
First thing you do is call the malloc.
And then we call the copy constructor. And then over there, we're allocating another space for T.
That's right.
So is it like what? It's kind of confusing for me.
I mean, that one's calling a constructor which is allocating space, but it's not space for set. It's actually space for elements array. Notice what the set is just 2 things, a pointer and an integer. Here we are actually blessing that pointer with an actual memory location. So now that we have this, by the way, we can actually do this a lot cleaner in that it's really just going to be new int this to the length of. And that's how the constructor can be written with a new rather than a malloc. And then the destructor can just call delete elements and then just take care of it. So you declared memory and you deleted it at the end. Make sense? Yep.
So, what's the use of the destructor underneath the hood for the delete? Because if you're gonna free that memory location, like in, if you're gonna free those areas in your heap anyway, why do you need to delete this?
So what's going to get freed is set. How many bytes is set? There's 2 things in set. There is a pointer to elements, 8 bytes, and then there's the length. When elements get freed, does it actually mean that what the pointer points to also gets freed? It does not. That's why we actually need the destructor. It's only going to remove the data members, but if data members point to something else that needs to be removed, you have to remove it in your destructor. Which is, like I said, easy to remember is if my constructor is calling new anywhere, I should have an equivalent delete in my destructor as a best practice. Make sense? All right. So yeah, there's a lot we have to cover still in C++, but one last topic that I do want to at least touch on, because it's pretty fundamental to the difference between C and C++. So one of the wackiest things that C++ has is that there's another type of special function. Remember we talked about constructor, destructor, and copy constructor? There is another type of C++ functions, member functions, which are referred to as operators. So inside my struct, and I'll just call it my set, I have 2 member functions, length and elements. I can do something else that's pretty interesting, and it's called, the concept is called operator overloading. I can actually change the behavior of operators. And what are operators? A plus is an operator, literally the plus symbol. I can change what plus means in C++ for a particular type of set. So earlier, if I did set A plus 3, what will that do? You'll just get a compiler error. The type is non-numeric. Now I can actually define the behavior that I want to exist. It's not going to happen by default, but if you want to say that it's called operator overloading, what that means is that I can actually overload the operator to say the plus operator when one of the sides is a set, I want the plus operator to do not just a numerical add, but do something else. And that's basically what the idea of operator overloading is. So in fact, one thing I want to just leave you guys with an important thought here, because this will help you with the exercises. So I can actually declare an operator. I can literally declare the operator plus, and this will change the behavior of plus if I wanted. I can really override any operator. So some of the operators that you typically override are plus, minus operators. Another one that actually is quite relevant over here, the square brackets. You can actually overload and override the square brackets operator and have it do something else for you. In fact, there's other craziness here. You can actually override the multiply, the divide, the unary minus, and whatnot. So that's where I think we'll pick up next Monday. And we'll actually go through what some of these operators, how operator overloading works. And my peers will probably cover this a little bit Friday. There's a small portion of the assignment that will require you to understand this portion. So you'll learn a little more on Friday for this.
Overload double brackets.